and this is the place where I work. So it's a transit campus. ISET Tirupati is one of the baby ISETs. You must all have heard about like ISET Pune, ISET Kolkata, Trivandrum, Bhopal, etc., etc. But ISET Tirupati is pretty new. We are currently working in a transit campus. This is, despite being a transit campus, it's actually pretty beautiful. This is the building of the transit campus over here. And you see, these are the Tirumala hills, like the famous pilgrimage hills over there, which are pretty close to the campus. And this is the basketball court. And you get good sports facilities, you get good food facilities, and you have good Wi-Fi. What more do you need in the place, right? You don't want like research classrooms and all that, right? Yeah. Sports, Wi-Fi, and food, right? Yeah. With that, it's a good enough place, right? Yeah. But of course, what's not shown here is also that we are building up a lot of good research facilities. We have high performance computer facilities and state-of-the-art facilities, each of which, if I just talk about it, will be an advertisement slide for ISET Tirupati itself, right? Which is not what I'm here for. I'm basically going to talk about the connection between chemistry and computers and the personal connection with your state. So I must tell you that roughly 15% of our students, right, they are actually from the state of Karnataka. But unfortunately, I just looked at the data point and I spoke with the students over there. There is no single student from Belgavi district yet. That's surprising, right? We have people from Shimoga district, a lot of people from Mysuru, Bidar, like Dharwad also, like Hubli, and all these places, but none from Belgavi itself. I don't know why. So maybe, like from this batch, perhaps we should be getting some students from ISET Tirupati. Alright, yeah. So, I'm introduced, this is what I do for my living. I work in the area of what is called as computational and quantum chemistry. So, which is, this kind of what I'm going to be talking about. Not exactly my research, but I'll give you a glimpse of what it means to do research, chemistry research using computers. About the rest of it, I won't talk today. So I have my own independent research, and this is my PhD student, I have a research grant, and he's one of my collaborators. I'm a theoretical chemist, which means, theory is nothing until you have experimental evidence. You agree with that? Otherwise, I can keep theorizing anything, right? I can keep theorizing that, I don't know, the fans under me and not above me and all these things, right? But experimental evidence suggests otherwise, right? So therefore, we collaborate heavily with experimentalists. And I'm also, partly interested in what is called as scientific pedagogy, which is an area which talks to you about, how to make teaching more boring. Okay, right? Yeah. So that's kind of my auxiliary interest. So I won't be talking about any of this in great detail beyond this slide. And what this slide is actually going to be about, what this talk is actually going to be about, I'll present in this slide here. The first thing is, it won't be it won't be monotonous. I want it to be interactive. What's interactive? It does not mean I talk and you sleep, right? Especially after, a heavy good lunch, and then, you've had enough food for pate and thought, right? Yeah. So now you hopefully get more food for the thought now, right? So we'll make it interactive. Interaction not amongst yourselves, right? Interaction between you and I, right? Yeah. That, and then here's a surprise. How do I know you're listening to me, right? So in between, right? In between this talk, I'll actually be asking you, some questions. Some questions. I'll be asking a lot of questions. But for some questions, there will be some kind of a pop quiz. Meaning, if you answer it correctly, you'll be getting a dairy milk chocolate. Are you clear? And I'm not lying. No, I got this for you. See. So I want to tell you that, okay, ek hai aur baki bang mein. Okay, right? Yeah. If you take all of it, it will fly all over the place, right? So the point is pay attention. There's at least, something to be had for paying attention, right? Yeah. And lastly, this talk, contains a lot of material from the internet. Okay, some of this could be possibly, copyrighted images, right? I acknowledge all of them, that I took it from the web, right? Yeah. But I use it only for educational purpose, and there is no commercial or no proprietary interest here. This is something you should all learn. That ye Google ka zamana hai, right? Whenever you take a source from there, you should always point out, you should give appropriate credit to the source, right? Yeah, it's important that you do it. Are we good, right? Yeah. So these are the facets of this talk today. So before this, you all heard about computers, right? Yeah. So when you hear about computers, what comes to your mind? What all come to your mind? Speak of computers, what all come to your mind? So you raise your voice. You just had lunch, right? Games. Okay, that's something that doesn't come to my mind at least, yeah. Just, possibly what all come to your mind. Speak of computers. Hello? Yeah, what's your name? Sorry? Hendrik, yeah, Hendrik. What comes to your mind? Programming, excellent. Programming is something. And then, what else? Yeah, what's your name first? Sandhani. Yeah, okay, Sandhani, what comes to your mind? MS Word, yeah, some sort of software, right? Yeah, excellent. And then, so programming, software, and then what else? Something else, come on. Calculation. Yeah, kind of, yeah, always calculations, yes. Somebody from behind. Social media, yes, definitely part of it. Yeah, which is part of software, right? Yeah. Somebody else, yeah, something else I'm looking forward, something very key. Yeah, bole, yeah.
Searching of unknown things.
Sorry?
Searching of unknown things.
Yeah, exactly. Searching of unknown things, which is part of the software, right? Yeah. Google gives you the software. Yeah, exactly, sir. What's your name? Yeah. Mohammed Kaif, yeah. You were the one who came up, right? Yeah, bole, yeah. Communication, excellent, yeah. But what else? Quickly. I'll give you a hint, okay? आप सब एक चीज भूल गए. We're talking about a physical computer, right? You're talking about, like communication software. But what's an important thing needed to facilitate it all? Sorry? CP, right? CP, monitor, mouse. What's all it collectively called? The hardware, right? See, it's important, right? Yeah. You spoke about the software, you spoke about, like the programming thing and the associated thing. But you need the thing itself, right? So that's kind of, like that's a, oops. Look at this actual. So there is pollution and all these things, right? Yeah. I'm surprised you didn't get it, right? Yeah. So you have like explosions, pollution, chemistry, colors, and all that, right? Yeah. So let me add one more thing, There's nothing in this world which is not a chemical. Can you actually think of something in this world which is not a chemical? Including yourself, you, your parents, your grandmother, this table. Everything is a chemical, right? Just think about it. This is a deeper philosophical point, but chemistry is everywhere. You like it or hate it, but you can't ignore it. Okay, yeah. So now just coming back to the title of this talk, what actually connects chemistry with computers? This is like I have computers and I have chemistry, right? Yeah. But what's the connection, right? That's kind of what we're going to explore into in this talk, right? Yeah. Before we do that, let's take a look into a brief and incomplete history of computers, right? Yeah. Computers क्या होते हैं, right? And what do we start with? And all these things. Before that, the first pop quiz. Who's this guy? Who said it first? Who said it first? Yeah, I'll give it to hydrates, okay, yeah. Because I heard him first, okay, I'm sorry, it's a bit unfair, yeah. But, because I don't have as many chocolates as all of you here. So thank you, here you go. Yeah, much more chocolates back, yeah. So who's he? How do you know him? Father of computer. How do you know that? What did he do? Wait, yeah. What's your name? Vaishnu. Yes, sit down. Yeah. So what did he do?
He discovered computer.
Like how?
Through abacus.
Sorry? Through abacus. Kind of similar, yeah, exactly. So what this person did was, way back. Okay. So, do you know what is the time of when did Hyder Ali live? Hyder Ali. You guys are from the state, but you should know when did Hyder Ali live. 1700? Tipu Sultan?
Yes.
So, a little 20 years after Tipu Sultan's death, right? Roughly 1790s, that's when Tipu Sultan died, right? Yeah. A little later than this, like this person, Charles Babbage, I don't know how to pronounce it, right? Yeah. This person invented something, called as, a difference-making engine, which is kind of your abacus, right? Yeah. And that was the precursor. That was the precursor to the modern computers as we know today, right? And make note that, and some further improvements were made. Until about, let's say, 1837 on. The key feature is that the computer back then was a mechanical device. You know what a mechanical device is? Like a gear, right? Let's say you have your car gear, or your bike gear, or your bicycle gear, right? Or there was no electrical component involved. You understand, right? The point was it was just a mechanical device. You have an arrangement of gears and levers, right? And using this combination of gears and levers, you could just get, get some things done easier. So the computer was entirely a mechanical device. What changed it all? Just look at the slide and tell. What changed it all? So the point is, the computer right now, what is missing? The computer was a mechanical device, I've told you, right? Currently, electricity changed it all, right? Which means what? In this slide, what does it come? Exactly, right? the minute, you'll soon learn in your 11th or 12th standard, something like that, about diodes and other things, right? Yeah. The minute, like semiconductors, transistors were built, right? What was purely a mechanical device, which was the computer, became an electromechanical device. You know what an electromechanical device means? It's like the input is an electrical signal, right? The input is an electrical signal and a mechanical action is produced, or vice versa. I do a mechanical action, right? And then an electrical signal is generated, and that results in some sort of an output, right? So then, what happened was that, like back in the 19th century, which is in the 1800s, the computer, which was purely, you can see, right? From here? Or am I obstructing your way? No, right? Yeah. The computer, which was purely a mechanical device, right? That went on to actually become an electromechanical device. Which means what? You could do things much faster, right? So then, once the semiconductor was built, then you had the first writable RAM. What is RAM? What does it do? What does it do? 1% of time. No chocolate for this though, yeah. Yeah, what does it do? It's common knowledge, right? Wait, what's your name? Saish. What does RAM do? It shows step-away files, right? Yeah. So therefore, while you're working at it, right? While you're working in a computer, right? Your RAM is helpful for you to work, right? Yeah. What's the difference between RAM and a hard disk? Yeah, hard disk is permanent, right? This is temporary, right? Yeah, good. So then, like the RAM was built in 1949, like so long ago, the first RAM. And then in around 1950, did you know the Turing test? Have you heard about the name Alan Turing? Anybody watched the movie Imitation Game? Okay, you should watch a movie, okay? It's called Imitation Game. It tells you about a scientist, okay? This guy's name is like Alan Turing, right? Yeah. If you're not knowing anything else, at least know this one, okay? Yeah. I'm asking you to watch a movie, okay? Yeah. So it's called The Imitation Game, right? It's about the life and the history of Alan Turing. Okay, right? Yeah. So this person, proposes something called as a Turing test. Do you guess what it is about? It's about artificial intelligence. We speak about this, right? Can we give machines human-like properties? Huh? This guy Turing proposed this test way back ago in 1950. 1950, right? Yeah. India was just 3 years old. The independent country India was just 3 years old back then, right? Yeah. So he proposed that artificial intelligence test in 50, and then the very first commercial computer, was invented in 1951 only, right? Yeah. And then later on, something called as a trackball was invented. Now, what's a trackball? Exactly, it's the precursor of a mouse. What we have a mouse, right? Yeah. So the thing is like your trackball, right? Yeah. So that was the mouse, right? Yeah. It is the precursor to a mouse. And after that, you have the first hard disk. See, permanent, only in 1956. Are we clear, right? So the point is, the computers have had a fabled history. First, what started as a mechanical device, then slowly, became more and more of an electromechanical device. And see where we are here, with all this fancy stuff, projector, like a laptop and all this thing, right? We've come so long ago, right? Can you guess, what motivated, all these improvements in computing? Why do we care? Will our lives be worse, if we didn't have computers? We didn't have a hard disk or something? Why did we care so much for the development of these computers? Somebody? Calculation, excellent, yeah. What about, what's his name? Shashank, yeah. Okay, what about calculation?
Sir, humans could not count on their fingers, so they thought of...
Exactly, yeah. So humans could not count on one finger, so you went to your neighbor's finger, you went to that neighbor's finger, right? And after everyone's fingers were exhausted, right? No more minds and fingers left, right? Yeah. You had to, invent something else, right? So the point is the following, you nailed it, okay, yeah. So the point is, the improvements in computer hardware, right? Improvements in computer hardware are actually driven by the need to perform increasingly complex mathematical calculations, right? That's it. It's a simple exercise, like something I used to do, when I was about approximately your age was just have this 2 plus 2, build this geometric progression. 2 plus 2 is 4, 4 plus 4 is 8, 8 plus 8 is 16, right? Yeah. You could do this mental exercise until you get tired, right? Yeah. And then move on to 3 plus 3 and so on and so forth, right? Yeah. But the point is, increasingly difficult mathematical calculations, right, are the drivers for development in computer technology. Always, almost always the case, right? Yeah. Now, before we go any further, I must all ask you this, okay? How many of you here like chemistry, Like chemistry? You like chemistry, man? Chemistry is awesome. You're not lying, right? Yeah, you can be honest. Like, do you really like chemistry? How many of you here like chemistry? Be upfront and honest. Okay, excellent. Yeah. More numbers than what I expected. Okay, yeah. How many of you here like math? Yeah, excellent. How many of you here, who like math but dislike chemistry, or who hate chemistry? Like math and hate chemistry. Reasonable numbers, right? Yeah. How many of you here, who like chemistry but hate math? It's okay, be honest. I only see 3 honest people. Yeah, nobody from here especially. But the point is this, there is no love lost, between chemistry and math, right? Yeah. In fact, way back in 19th century, look at this guy. His name is Auguste Comte, a French person, but a prominent science philosopher. You know what a science philosopher does? He talks upon, what science is for the society, and what is the philosophy behind each science, and how it is useful for the common public, etc., etc. And what this person said was, every attempt to employ mathematical methods to study chemistry must be considered profoundly irrational. So all those 3 people, right, who like chemistry and who hate mathematics, this guy is in complete agreement with you, right? He says that, it is like, kya mathematics, kahin bhi mathematics, right? What's the point in bringing in mathematics everywhere, right? It's chemistry, it's my territory, don't get in, right? Yeah, that's precisely what this person says. And he just doesn't stop with that. He says that if mathematical analysis should ever hold a place in chemistry, it's an aberration, which he said is almost impossible, right? And it would lead to a degeneration of that science. Which science? Chemistry, exactly. Matlab kya hai? Mathematics again, chemistry, if we use it, right, chemistry sar jayegi. That's precisely his point, right? Yeah. That is, he nails it. That is his point, right? Yeah. But this was when? This was the 19th century thought overall. Math is absolutely useless in chemistry. Have you got it, right? Yeah. So, then again, right, then how come computers be useful, right? After all, right, we saw that the need of computers, right, the need for computers is actually driven by the need to do complex mathematical calculations, right? Yeah. But when, math is not at all useful in chemistry, right? Why do we even care about computers? Are we clear, right? This is the conundrum we have, right? But then, this is what happened. Remember, this was in 19th century, right? This was around, the Mangal Pandey period, 1857, this was a time when Gandhi and Nehru were all kids, right? Yeah. The nation builders, right? Yeah. But then in the 20th century, right? When we talk about the 20th century, well, chemistry was forced to use math. I'm sorry, ma'am. Okay, right? Yeah. So what happened was that suddenly there's something called as quantum mechanics. Have you heard the name quantum mechanics? Yeah. Do you understand it? Just say, somebody say yes, please. Yeah, you understand it? A little bit. Excellent. I understand the same little bit. Okay, yeah. That's what I want to tell you. Okay, yeah. So the point is the following. Okay, right? Yeah. Something called as quantum mechanics changed the complete, rules of the game. Right? What happened? In a funny way, it's kind of a family feud. Okay, yeah. So you must have also heard this phrase like wave-particle duality, right? What's wave-particle duality? Yeah, something is a wave, something is a particle. This, yeah, you must have all heard about, right? If you're especially in 11th standard, you must have heard about this, right? Everybody saying something and nobody understanding what it means, right? Yeah, be fair, right? That's what it is, right? Yeah. So that's precisely what happened. Based on some experiments, this guy, J.J. Thomson, is a Father Thomson, right? Yeah. He said that, the electron is a particle. He did some experiments, right? Let's not get into the experiments. No, it's for some other day. We can look into the experiments. And he said that electrons behave as particles. His own son, right? I don't know how much hatred this guy had to his father. He said that, no, Dad, you're absolutely wrong. Move away, you're old. Okay, yeah. The point is, the electron is a wave. It sounds bizarre, right? So, in the very same family, they had dispute about whether the electron is a wave or a particle, right? Yeah. And now, not just that. These people were experimentalists. The minute, I tell you, the biggest advantage of math is that whenever people have, a confrontation to describe something, mathematicians jump in. And they're like, you know what? No, forget it. Forget wave, particle and all this. Let's use some awesome math to describe it. Are we clear, right? But still, why worry about it all in chemistry? Okay, electron can be a wave, a particle, but why care about it in chemistry, man? Somebody? Hello? Why do we worry about this fact, electron being a wave or particle in chemistry? Yeah. What's your name? Raksha, yeah.
Because it is an electron which takes part in the chemical.
Precisely. Awesome. That's it. Yeah. So the point is, what is chemistry? You know, the way we've been seeing it. Chemistry is the making and breaking of bond pairs, right? It's all about, you know, like the affinity between electrons, right? Chemistry, right? Yeah. We name any reaction. Have you heard about the 11th standard, right? SN1 reaction and all that? Or SN2 reactions? Or name a chemical reaction you know right now. Name any chemical reaction you know. Okay, we know the mechanism of any chemical reaction. Anybody? No. What about say, okay, what about like, imagine, you know, like, do you know H3O plus? Have you heard about H3O plus? Okay, any chemical reaction that comes to your mind. Raksha, any chemical reaction which comes to your mind. Yeah, go ahead.
Displacement reaction.
Excellent, displacement reaction, right? Give an example of it, yeah.
CuSO4 plus Fe is equals to FeSO4 plus C.
Yeah, excellent, right? So what's happening there? You know, like Phi, Java and Ku come, right? Yeah, Phi is going and C is coming in, right? Yeah. What do you mean by that?
Stronger displaces the.
Yeah, but what is the chemistry happening there? Have you guys heard about oxidation numbers? What is the oxidation number of like my Fe and FeSO4? Fe and FeSO4, what is it? Yeah, well, plus what? Plus 2, right? Exactly, right? What is the oxidation number of Fe in like the product Fe? 0, right? All, you know, like elements in the natural state have a 0 oxidation state. So plus 2 became 0, right? What is that? That is a gain of electrons, right? You understand? Similarly, what about copper? Copper was copper, Cu0, right? That became copper sulfate, right? Cu to CuSO4. That became, you know, like it gained electrons, right? Cu, right? Or is it the other way about? Fe, right? Fe plus 2 plus 2e minus gaining Fe, right? Cu becoming like Cu plus 2 plus 2e minus. So the point is, chemistry is essentially the making and breaking of electrons, right? Breaking electrons and making electrons is all about chemistry. Are we good with this, right? So therefore, chemistry cannot escape math because the entity which like is used to describe chemistry, right, is behaving funkily. Are we good with this? So therefore, what's the bottom line? Well, unfortunately, chemistry has to use math, right? Yeah. Now, you know, like let's just look at, you know, like don't get scared with this slide. Okay, let's just look at a simplified version of the math used to describe the electron. Have you heard this equation before? What is this? It's not as hard as it sounds. Okay, I make it look fancy. Okay, yeah. You heard about some equation called the Schrodinger equation, right? This is the Schrodinger equation. It is nothing but a partial differential equation. It's easy, right? See, I'll tell you what, I promise you, okay? You're in your 11th standard, right? By the time you finish your 12th standard, you'll be like, this is just another partial differential equation. You'll get to know it, okay, yeah. But the point is, you know, like, excuse me? Is it working? This thing. Might be okay. Thank you. Right. So the point is, right, yeah, this is a simplified version of math used to describe the electron. It's called as the Schrodinger equation, right? And have you all heard about something called as the wave function? What does it mean? Yeah, what's your name? Yeah. Sorry? Nandini. Yeah, so Nandini, tell me, you know, like, yeah, what does the wave function mean? Almost there, okay, and then? Anybody else? Yeah. What does the wave function mean? You're almost there, okay, yeah. What does the wave function mean? I'm going to ask you to repeat this after me, okay, right? So you must have all heard the phase wave function, right? In your schools, you must have heard, right? Like while talking about these quantum numbers and all those things, yeah. But you know, when you ask about what the wave function is, what's the standard answer? You'll learn about it later, right? Yes or no? Hey, have you been to your school in 11th or not? Yes, right? Have you studied atomic structure or not? Yes, right? Then why the silence, right? Yeah. So you must have heard about this phase wave function, right? Absolutely. What is it? She said that, you know, it's related to the probability, right? That's Raksha's answer, right? What's your name, sorry? Nandini's answer, sorry, yeah. Yeah, what's your name? Shruti, yeah.
The energy is required to eject the electron from the metal substance is called wave function.
Okay, so yeah, so we have like different thank you, sit down, okay, yeah. So you kind of there too, like she's connecting the photoelectric effect with the wave function, right? Yeah. The point is you're almost there, right? What are you all trying to do? You're all trying to, this word, okay, this English word called wave function, you're trying to connect it with some physical interpretation. Are we clear, right? That's kind of what you're doing, right? Are you good with this? Now, you're going to repeat after me and take it to your heart, right? That the wave function has no physical meaning. Repeat after me. Now take it to your heart, right? I don't know how to do it, but you understand what I'm saying, right? Yeah. The wave function has absolutely no physical meaning. It is a construct, right? It is a mathematical construct, which is nothing but, like a solution to this equation. Are we good, right? For example, like I give you an equation, x squared minus 2x plus 1 equals 0. What is x? X equals x, you can find x, right? X may be 1 here, right? Yeah, x may be 1. For some reasons you can find x. But what is the physical meaning of this x? How do you know, right? Yeah. What do you mean? What is the physical meaning of 1? Or 2, right? Yeah. That's the point, right? Yeah. You can of course get some solution, right? But the solution need not have any physical meaning, right? It's a very common misconception, okay? A very popular one, right? That of associating, okay, a meaning with the wave function. So the wave function absolutely has no physical meaning. What is it? It is obtained as a solution to some mathematical equation. Are we clear about this? See, if not like any other take-home message, okay? I want you folks to be clear about this one, right? Yeah. The wave function does not have any physical meaning. What does it mean? It means that, okay, you all do experiments, right? Can you do any experiment in the world to get a wave function? No. Right? As a result of no experiment, will I get the wave function ever? The wave function is a purely mathematical thing, right? You already saw, right? Now, we're talking about chemistry. The wave function is used to describe the electron, but then it is not physical. It's all mathematical, right? Imagine how much mathematics is included into chemistry, right? In just about 2 slides. Right? Yeah. Unimaginable, right? Yeah. We'll come back to this point. And see, you must have all known about these quantum numbers, right? Everybody has listened to the quantum number, right? Yeah. Anybody here who's not heard about quantum numbers? Raise your hand. Anyone here who's not heard about quantum numbers? Okay, you all go to schools and you're all good students, right? Yeah. So you've been listening to your chemistry teacher and you know all about these quantum numbers. And interestingly, some quantum number is missing here, right? Let's not worry about that, okay? That comes a bit later. But the point is that associated with each of these quantum numbers, I have a particular wave function, right? Now, what orbital does this correspond to? N equals 1, N equals 0, M equals 0? What is it? What orbital is this? 1s, right? Yeah. So corresponding to my 1s, like orbital, I have a wave function, which is called as psi 100. You understand, right? Yeah. Similarly, corresponding to my, like n equals 2, n equals 0, I have lots of wave functions. You understand that, the mathematical form of these wave functions is becoming more and more complicated, right? As we just go along. These are all nothing but solutions, right? 2 points to note on that. They're getting more and more complicated. And not just that. What's this guy right here? If you look at, let's look at, like n equals 2, n equals 1, and ml equals plus or minus 1, right? You have this guy right here, right? What is this? Can somebody say it aloud? What is it? This one, e to the power, what is this? Plus or minus I? I phi, right? What is I here? Have you had complex numbers? Square root of minus 1, right? Wait, so the wave function, right? The wave function contains a complex number. How can it be real, right? You understand? So the point is, but why should it have complex numbers? It's obtained as a solution to some mathematical equations, right? I cannot control. You know what? Given my mathematical equation, मुझे जो solution चाहिए वही आना चाहिए, right? वो जो आएगा वही आएगा, right? Assuming you're doing the right math. If you do the wrong math, of course you can do anything you want. Yeah. But assuming you do the right math, right? I don't govern what solution I get. The rules of math governs it, right? So therefore, the wave function can have stuff like, imaginary numbers as part of it. Which naturally tells you that, give me again an experiment, which gives you stuff which contain imaginary numbers. No, right? The wave function is again purely mathematical, right? And associated with each of these orbitals, right? Associated with each of these orbitals, we can have a wave function. And the wave function gets complicated, right? Now you understand that. See, for example, when you get to the n equals 3, l equals 1, and ml equals plus or minus 1. Look at this expression, right? Reasonably hard, right? Yeah. And this is nothing but a simplified version of the math. I've skipped so many details, right? Yeah. I've skipped so many details, and even in the simplest version, we have this many complications. Which means what? Mathematics is telling chemistry, hut jao, ab nahi bari hai. Right? Yeah. So mathematics has completely invaded chemistry. That's kind of what it is, right? Yeah. And not just that. See, one more thing. So, have you studied shapes of orbitals in your school? Right? Yeah. So, you know, like, do they teach you about the s orbital shape? Do they teach you about the p orbital shape? D orbitals? Kind of yes, right? F orbitals? Somebody said yes. Does it teach you? No, right? Why no? Why is it complicated? Because the mathematical function or the wave function becomes too complicated to plot and understand something. You understand? That's why, right? That is the actual reason behind it, right? So the point is the following, from the message from the last slide and this slide is that even the simplified version of the math, okay, used to understand the electron can become very complicated. Which means what? Which means what? You need to use computers somehow, right? Yeah. So we'll get to this point again. Now, here's the second pop quiz, right? The David Milpala quiz, okay? I want you all to tell me, who this person is. He looks like Charlie Chaplin's cousin, okay? In this picture, but he's not here. So tell me who this person is. Somebody? Do you have the habit of Googling and Wikipediaing? Who this person is? No, not Alan Turing. Good guess, yeah. I'll give you a hint, okay? He's a physics Nobel laureate. A physics Nobel laureate. Yeah, I'll give you one more hint. One more hint that you know. How do I give it? He's a super smart person who started off doing engineering and who found that pure engineering itself is useless, but engineering techniques applied to science is wonderful. Do I wait? Yeah. Who has Geo? We can look at him. Look up, right? Yeah. Who's this person? Yeah. Sorry? Sure. Sorry. Henry Mosley. No. Fair enough. Yeah, but not him. Okay, I think this was a tough one. Okay, yeah. Let's skip it. Okay, we'll come back to it. This person is called as Paul Dirac. Heard the name? Paul Dirac. Paul space Dirac. Heard this name before? Look it up. So look him up. I think as part of this talk, you should also be inspired, right? To actually look up some real scientists. Okay, his name is Paul Dirac. Okay, look up to all the things he did. He made one beautiful statement. Which says, besides this, of course, yeah, we'll come back to this statement. But in a small digression, the statement he made was, what is the difference between poetry and science? Poetry is also awesome for some people, right? For science is also awesome for some other people. What is the difference between the two? He said that, science strives, to make difficult things look easy. You understand, right? Whereas poetry strives to make easy things look difficult. This is a profound point, right? Yeah. If you think about it, right, that's what it is, right? Yeah. It's a profound point, and he kind of, made his allusion between the comparison between, science and poetry. Yeah. But that aside, he made one more statement. He said that in 1929, he made the statement. He said that, the physical laws, and the mathematical theories to study whole of chemistry has been made already, right? He says that, he effectively says that, we know all the math. We know all the math, meaning all the equations which need to be solved, that we know. The only thing we can't do is to solve themselves, because not enough fingers, not enough minds, right? Yeah. So we must somehow come up with approximate solutions, approximate practical methods, such that we can somehow solve it, right? The crux of the statement is that understanding chemistry requires a lot of difficult and tedious mathematical equations, right? So what to do? Dimaki Bati, right? Yeah. So that is over here, and the answer is that we can use computers to solve otherwise unsolvable equations in chemistry, which means that, the connection between chemistry and mathematics is made complete by computers. Are we clear? Right? Yeah. So then, yeah, what are these equations? We speak about some equations, and how difficult they are, and why do we need computers, right? This slide kind of explains why. Now, look at this thing right here, right? It's just a hydrogen atom. One hydrogen atom has how many electrons? One electron. And how many nuclei? One nucleus, right? Yeah. Forget the isotope distribution, okay, yeah. So if you just take a look at like hydrogen, we have like the nucleus over here and the electron over here. The nucleus shown as the bigger ball and the electron shown as a smaller ball. This is just a representation, this is not reality, okay? In this representation, you know that, to solve this equation, you just need two terms, right? You just need two terms. Now, you have something, you take something called an H2 plus. What is H2 plus? H2 and an electron removed from that. So I have two hydrogen atoms, but still only one electron, right? You understand? In this situation, already, the number of terms required in the equations increase, right? If you're interested about how these terms come up, talk to me later, okay? I'll explain it, yeah. It's just, like, have you had conservation of energy? Conservation of total energy in classical mechanics? It is nothing but it's quantum mechanical deviation, okay? This term here represents the kinetic energy, this term here is the electrostatic energy, the potential energy, and both put together is the total energy, right? And we have to include, some other terms to solve this equation. But the point is, even with just hydrogen, now look at hydrogen atom. A hydrogen atom, right, H2, instead of H atom, if you take, hydrogen molecule, if you take H2 molecule, now you have like the number of terms increases much more, right? Just from H to H2, number of terms increases massively. So therefore, the point is that as the equations contain more and more terms, say imagine I'm dealing with benzene, right? Or let's say a DNA molecule. Number of terms will be what? Much, much more, right? So to deal with it, a computer is the best way. Are we clear with this, right? Yeah. So the point is, as the number of terms in this is called as the Hamiltonian. Okay? It's just a fancy word. For an equation, right? Which we're going to solve, right? So as the number of terms in this equation increases, we can do nothing by hand, right? We need a computer. So therefore, we solve by computers, right? Yeah. Now, one more pop quiz. Let's see who answers this one. Look at this term right here. What is it? Minus h bar square divided by 2me, where me is the mass of the electron. And I have something here called as del square, right? Are we clear? The pop quiz is the following. So what is h bar? H bar is nothing but h by 2 pi. You all know what h is, right? What is h? Planck's constant, right? Good, yeah. So h is the Planck's constant, and what is pi? Pi is just a number, right? The irrational number pi, right? Yeah. Now I'll tell you that, and what is me? Me is the mass of electron. I'll tell you that, this whole thing, minus h bar squared by 2me into del square, right? It has units of joules. You understand, right? Minus h bar squared by 2me times del square. The whole thing has units of joules, right? The question is, what is the unit of this del square in SI? Is the question clear? The whole thing over here, the whole thing minus h bar squared by 2me times del square, it has units, okay? It has units of joules. What is the unit of del square? Work it out. I'll give you about 30, 40, 50, 60, 70 seconds. Pardon? Per kg per second. Nope. So one answer is eliminated. What is the unit of del square? Quick. Think. Have a good lunch, right? Should active. Your brain should be active. Come on. See, whenever anybody asks you to solve something, take a pen and a paper, don't discuss. Right? That always helps. Quick. The first person to answer it, right? Yeah. Minus h bar square by 2me times del square. I'll tell you that the whole thing is in terms of joules. What is the unit of del square alone? Yeah. You answer it? Yourself, yeah. Joule per what? Nope. Yeah, what? Second. No. Yes, let's say I'll go for 5 more, let's say 6, 7 more options, and then I'll call it a day. And then I'll tell you what it is. Quick. It should also be thinking, right? Yeah, come on. It's not that hard. I'll give you a hint. What is the unit of h bar? What is the unit of h bar itself? J's, right? That's a hint. Yeah. Excellent, yeah. So, mass is in kilogram. Yeah. Oh, you say del square has units of mass. No. Work it out. I won't cheat. I'll give you 2 dairy milks. Yeah. Quick. Per. Well, be careful. Be careful. Yeah. Sorry. Per second? No. You be a bit careful. Okay. Yeah. What did you say? Meter second. No second. Sorry? Yeah. No kg. Sorry. Yeah. It's easy, man. It's del squared. Okay, that doesn't matter. But that is not del squared doesn't matter. But like, sorry, you're almost there. You deserve, like a dairy milk wrapper. But the difference between, like 2 dairy milks and a wrapper is going to be the right answer. Yeah. Sorry. Well, excuse me. Is it meter square? Is it meter square? Yeah. You know what? Okay, I'll give equal to dairy milk. Okay, it has to be per meter square. N to the power minus 2. Okay, yeah. You have one. I think it's the second one, right? The first one you were lucky. Yeah. And you get one. Thank you. Yeah. So how do it's straightforward, right? See, the point is this. Okay. You assume it is per meter square, right? If you assume it's per meter square, right? What is all this? All this is equal to joule square second square, right? Joule square second square divided by kilogram meter square, right? Joule square second square divided by kilogram meter square, right? I say that is equal to joule. You cancel out the joule on both sides, right? Which means you take the kilogram meter square second to the power minus 2. That is equal to a joule, right? E equals half mv square. You understand? So it has to be, therefore it has to be per meter square, right? So I gave you the chocolates, but your friends have all reasons to be upset because both of you are not right actually. Right? Yeah. Remember that. Okay. So the point is the following, okay. These equations, right? And see, it's all straightforward, right? It's not that hard. The term looks unknown to you, right? But the minute I start talking in terms of units and dimensions, right? It's all something that you're familiar with, right? Huh? So that's what it's all about. Like the words are fancy, right? Don't get caught up with fancy names. The concepts are simple. Focus on the concepts, not on the name, right? Yeah. So we need a computer to solve all these difficult equations. And what is typically done? In this branch of using computers to solve all the difficult equations in chemistry is actually called as computational chemistry, right? Yeah. So what does this field do? In this computational chemistry field, what is typically done is that you have a molecule, right? The input to a computer is actually a molecule. So what do? You put the molecule inside a computer? What do you do then? Pardon? You input the coordinates of a molecule, right? Everything has a set of coordinates associated with it, right? Like Professor Kiran Kumar was saying in the morning, right? About like your latitude, longitude and your coordinates, right? Everything has a coordinate, right? Yeah. So the molecule also has its own set of coordinates, although in nano dimensions, right? How tiny is the molecule? Like very tiny, right? Have you seen Stuart the Little? Yes. Yeah, imagine, don't do it, but squeezing him, really small, right? So that you get nano Stuart the Little, right? Or like atom, something like that. That's kind of what it is. Do you know what is the bond length of a hydrogen atom? Bond length of an H atom is roughly of the order of 1 angstrom, right? Yeah. So it's roughly of the order of 1 angstrom, right? So the point is, the dimensions of the atoms are in the angstrom scale, right? We are living in, let's say, 10 to the power minus 10 times our scale, right? Yeah. So you input the coordinates, right? You input the coordinates of the molecules, and then what happens is that you tell the program what it wants to do. The program already has, meaning when I say the program has, we the computational chemists, we code in data about okay, what is it you want? What equation do you want? I'll write a program to solve it, right? We'll write appropriate programs to solve, for whatever we want, for whatever molecular property we want, right? Yeah. So then once we get these molecular properties, we can interpret them, right? Are we good, right? So it's a simple world as it looks here, right? Simply give an output as a molecule, and then as long as I know how to write appropriate programs to solve the equations, I can always get some properties and I can interpret the results, right? But there's a small catch here. The point is, how do I know I'm correct? Computationally, I can get anything I want, right? Theoretically, I can say that, I don't know, the sun is the moon. I can say whatever I want, right? Yeah. Theoretically, I can say there's no end to the nonsense I can generate with theory, right? The point is, therefore, anything that is only verified by experiments, only that makes sense. Are we clear, right? It's only post-verification with experiments that we can say whether whether our theory makes sense or not, right? Let's look at an illustration for that. Say for example, you all have like heats of formation calculation, right? How do you calculate the heat of formation of a molecule? Any idea? What is the experiment used to calculate the heat of formation of any molecule? Bomb calorimeter. Heard about it? Not yet. Okay, you'll soon listen to what is called as a bomb calorimeter, right? So you can maybe in physics or chemistry, I forget the word. Okay, yeah. But you can calculate the heat of formation of a molecule. Now shown in this slide, right? Shown in this slide, are the experimentally calculated values, right? Now shown over here, all these other things, right, are different values, right? Calculated using different approximations. In theory, we understood that we have to make approximations, right? So using different types of approximations, I can get the different numbers. Now, depending on how good my theory is, I can either get really good numbers, which are shown in the blue here, right? 544, this is 542, close enough. 203, 204, close enough. 21, 22, close enough. 164, 162, close enough. Well, close enough in these two cases also. But look at this one here. It's so awful, right? It's 544, it's 492. 203, 214. For this guy, it says 21, it says -3, right? It says -3, and then like for 164, 149, 365, 391, 563, 619, the disagreements are huge, right? In that case, if you assume that the experiment is done carefully, that's important, right? Yeah. If you assume that the experiment is done carefully enough, you have to trust the experimental value, and the point is this: theory can guide, but experiments are the ones to decide. Always, right? For example, like the best example is like, say you're hungry, right? And you want to eat like, you want to eat some masala dosa. You can always look up, you can Google how to make a masala dosa. But that won't satisfy your appetite, right? You have to actually make a masala dosa and eat it, right? Yeah, that's when the experiment is complete, right? Likewise, you can do all these theoretical things, which is extremely useful. Because if you don't know how to make a masala dosa, you still have to look up the theory, right? You may end up, like wanting to make masala dosa, but end up making black carbon, right? Yeah. If you don't know, so you have to properly look it up. And once you've looked it up, then you look at it all, right? Yeah. Now, one more pop quiz. You look at this molecule right here, right? CH4 giving CH2 plus H2, right? What is this molecule CH2 known as? CH2. What is CH4? Yeah. Everyone knows that, right? Yeah, no dividend for that, okay, yeah. So what is H2? Hydrogen, of course, right? Yeah. What is CH2? Oh, wait, I heard it. Somebody, yeah, some girl said it, yeah. What's it? Methyl what? What's it called? Yeah. What did you say? Methyl what? Of course it's methyl, yeah. What species is it? So how is it formed? You have methane, right? It's formed by the homolytic cleavage of like two hydrogens going away, and you get methyl what? Methylene what? Group, what is it called? Sorry? Free radical? You're almost there. A free radical is what? A CH3 dot. See, you have CH4 giving CH3 plus H, right? The CH3 over there is a free radical. But I have CH4 giving, like CH2 plus H2. What is this called? You want a hint? It begins with C. It's a general, yeah, it begins with C. Who said it? Ma'am. Not fair, right? Half of the room, but like, but the tango didn't listen to it. What's it called? Yeah. What's it called? It begins with the C, right? Ends with an E. CE. And has like 7 letters. Sorry? Okay, you know what? I'll take one too. Okay, this is called a carbene. Okay. This is for me, right? Yeah. So this is actually called a carbene, okay, yeah. Alright, yeah, we're getting over close to the answer, right? Yeah. Okay. So the point is the following. Don't believe everything a computer gives you, right? So just because, like you have some Apple Watch or something, and then it says like, okay, it's time to jog. Don't believe in it. If it's 5 a.m. and then you wake up, it's time to jog, right? Yeah. Don't believe in a computer blindly, analyze it, right? Just because your Facebook suggests that, okay, this person has to add me as a friend, okay? Don't add that person immediately, right? Think about who it is, right? Yeah, before doing these things. So theory can always help you, but I want you to understand that experiments are the ultimate standard. This is coming from some person who doesn't do experiments. I do computational chemistry for my living, right? But even then, experiments are the ones which ultimately decide how meaningful any theory is, right? Yeah. So let's just look at, let's quickly go through some examples of what this field was way back in the 1970s, right? This is a popular software called as the Gaussian program, right? Yeah. Way back in the 1970s, you could do, you could calculate energies and molecular properties for small molecules. It's a small molecule, right? It's called vinyl cyclobutane, right? This was the status in the 1970s. Now, let's say, in around 1980s, right? Around 1980s, you could deal with like medium-sized inorganic compounds, right? The complexity of the problem is larger, right? Yeah. Then, you go back around 1990. I don't want to focus much on the details of the slides, just this part alone. So we have a DNA polymer, right? We can deal with large bioorganic molecules. Then now, around 2000, you can deal with a molecule as big as this. This is called as rhodopsin. Heard the name rhodopsin? Anybody? Rhodopsin? Have you heard the name rhodopsin before? Yes or no? In what context? You said no. So can you see me? This molecule is responsible for that. Right? Your homework is to figure out why and how. Right? How can you see me because of rhodopsin? Right? Yeah. So figure out how rhodopsin is responsible for you seeing me and me seeing you too. And of course, wearing my glasses also help. Okay. Yeah. So anyways, this is around 2000. And now see, way back, more recently, in around like 2009, we can deal with a huge molecule. What is isopenicillin N synthase? It's something, which is useful whenever you get like some malaria or something, infection or something like that. This enzyme, right? This enzyme, which contains thousands of atoms, right? It is super useful, like in dealing with your immune system. I don't myself know exactly how, right? Yeah, you can figure out. But the point is, it's an important molecule, and its simulations can be done theoretically using a computer, right? So imagine, in 1970, we had to deal with a small molecule. From then, how long have we come to, right? Yeah. So, not just this. Okay, time for one more pop quiz, okay. So, have you understood, do you all understand, like in chemistry, people speak about mechanisms? Have you heard something called as a chemistry reaction mechanism? Yes or no? No, right? You'll soon get to know, like when you study like your, have you studied Lewis structures and all that? Okay, you'll soon get to study them, okay, I'm sorry. Okay, when did the school start? June, July? So starting from June to until September, what have you learned in chemistry? Like chemical bonding maybe? Chemical bonding, which is Lewis structures and all those things, right? Organic chemistry, not yet. When did they start organic chemistry? Yes, right? Electrophile, nucleophile? Yes or no? Okay, but the point is the following, okay? You can always study, then the pop quiz is cancelled because it doesn't make sense, okay, yeah. I was about to ask you, like what is this name of the reaction here? It's called the Thiel-Zarda reaction, okay, yeah. But unless you know organic chemistry, it's a bit difficult to understand this. And again, the point of this slide is that, what theory does is, how does a chemical reaction happen? Have you heard the phrase transition state? What is a transition state? It's like, it's nothing but this, right? Jack and Jill went up above the hill, right? That state is called as, like transition state. Whenever chemical reactions happen, you know how it happens? Molecules collide with one another, right? So when molecules collide with one another, what happens is that in some cases the energies of the molecules go up, right? And when you have a high enough energy state, right, that is called as a transition state. It's a very crude representation, but I'm just informing you. Now from that high energy state, molecules fall apart in one particular direction to give you the products, right? So this is called as a transition state theory, right? Yeah. So these transition states, they are unstable, right? Using experiments, it's almost impossible to locate them, right? So theory is of immense help. Theory is of immense help in locating these transition states. And to do these theories, you need what is called as computational chemistry. Are we good? Yeah. Don't worry if you don't understand the chemistry behind this slide. But all I want to tell you is that there is something called as transition states, which are super hard to get experimentally. And theory and computational chemistry is very useful in getting that. So therefore, even though we don't do any experiments, the math is super useful in chemistry in the context of helping chemistry, which experiments are difficult to get to, right? Yeah. And not just that. There's one more thing, see, so far, we've been speaking about the academia, right? Like all academic pursuit, reaction mechanisms, and then reaction mechanisms, like chemical structures and all these things. does it find any use in the industry, right? Ultimately, मुझे कुछ काम चाहिए, right? Not everyone becomes a teacher, not everyone becomes a scientist or a researcher, right? People also go to the industry and do great stuff, right? Even in the industry, for example, we have this whole area called as computer-aided drug discovery, right? In this area, so you can have somebody who's asking about coding, right? You can write your own program. You can do your own program to actually help in drug discovery. You can choose what structures you want. You can choose what structures you want. You can study toxicity effects. You can also, understand metabolism. You can understand various aspects of metabolism, and all this goes hand in hand with biomedical applications. You understand, right? So this field of computational chemistry is wide enough to not just include academia, but also, like the industry, right? So where did we go from? So far, we were like, we thought that, chemistry, had nothing to do with math to begin with, right? But then later on, we understood that, better computers are needed to do more tedious math, and quantum mechanics forces chemistry to use computers, right? Yeah, right? That's one thing. And not just that, computers are extremely useful to do the math because we just can't do them, right? So therefore, when we can't do it, we kind of let the computers do the job for us. And we also saw some examples of computational chemistry, right? We saw some examples, and I must confess that these examples are rather vague because I didn't spend a lot of time on them, right? It was intentionally vague because you need to actually know a lot of chemistry and computations to actually understand computational chemistry. Right now, we can just see, that it may be useful in some context, right? Yeah. This is what we did so far, okay? Now is the time for another pop quiz. What is the title of this talk? One person said correctly, exactly. Are you paying attention? What did you say? And no, almost? Yeah. You're almost there, missing one phrase, yeah. Wait, yeah, what did you say? I wanted exactly. It's for the dairy milk, right? I wanted the exact thing therefore, yeah. Well, almost, yeah. Yeah, somebody, yourself, yeah. Yeah. Exactly, yeah, the hidden connection between chemistry and mathematics through computers, right? Yeah. So there you get a dairy milk, okay, yeah. So, I won't come there. I'll give it to her. Hopefully she passes it along. Okay? That's not my responsibility, okay, yeah. To that girl. Yeah. Alright. So yeah. So now, we look at some hidden connection, between chemistry and mathematics through computers, right? Let's actually look at a few more connections, right? A few more connections of a different type though. Right? Yeah. I think, this is a super important part of the talk. Okay, yeah. This is what it is. Okay, what do you see in this picture? Forest, right? How many say forest? Raise your hand, yeah. You see forest, right? Excellent. You said something else. See, he's saying a tree, right? You're seeing a forest. So are we seeing a forest or a tree? Tree or forest, right? Yeah. So let's look at, yeah. So you have is it a tree or a forest, right? Yeah. This is something super important, okay? I'll tell you why so in a minute, okay, right? Yeah. The point is this. If you go to any dictionary, the dictionary I used, okay, it says that a forest is a large area covered chiefly with trees, right? Yeah. So the forest has trees, and trees are in forest. Okay, yeah. But in life, right, we use this example to use this as a metaphor. The forest is a metaphor for the bigger picture, right? You understand what a bigger picture is? I'll get to it soon enough, okay? The next slide I'll explain what the bigger picture means. And likewise, the tree is a metaphor for the details making up the bigger picture, right? So there are always two things, right? Let's say if you want to go home, right? You want to go home, well, the bigger picture is to go home actually. What are the details? To take the right route. If you mess up your details, right? You can still, you'll never go home. But if you do all the details right, there's still no guarantee that you actually reach home, right? So in life, the bigger picture and the details are both equally important, and they're referred to as the connection between the trees and the forest, right? Yeah. Now, let's look at this. How many of you here like the movie Bahubali? Yeah, only so few? Alright, I'll tell you, yeah, okay, thank you. See, hands are slowly rising up, reluctantly slowly, okay, yeah. When I said, how many of you like chemistry, the hand rising up was at much lower rate, okay. Which is expected and fair, okay, yeah. The point is the following, you focus on this scene. Remember what scene I'm talking about? What is this scene? Sorry? What is this scene about? War with whom? Which ones? There are too many people, right? The Kalakayas come, and then the other ones also come. Who are these people? The Pindaris, right? Yeah. So then what's happening here? So like this Bahubali guy would help, like this Devasida's kingdom, right? In the fight against the Pindaris, right? Yeah. When does it happen? In the night, right? It happens in the night, right? Now the point is the following. When you say the forest, right? The bigger picture, it means the overall scene, right? Yeah. And the idea that Bahubali uses cattle to defeat the enemies, right? That's the whole point. It's about like, how do I best describe it? But what are the trees and the details which make up? The details are absolutely, like worthy of mention. This is happening in dark, right? So therefore he should show the moon, right? He can't show the sun, right? Yeah. So the details which make sense, right? That's one detail. The color combination. Say for example, if Bahubali were also wearing, the night is dark. If you're already wearing, like a dark shirt, you wouldn't see anything, right? The red contrasts it beautifully, right? And then you see the fact that, like the horns of these cows, or buffaloes or whatever, right? Yeah. Not buffaloes, like bulls, yeah. Yeah, right, yeah. Or white buffaloes, yeah. So whatever they are, right? Yeah. They're having light, right? They all add meaning to the scene, right? The point is, to accomplish anything, like of a bigger nature, you have to go through the details, right? It's something super important, right? Yeah. In this thing, so, like, what are some, like trees and forests in science, right? Forget Bahubali, okay? It was just for one slide, okay? To get you away. And yeah. But the point is, like with anything, not just in computational chemistry, in the whole lot of science, and in fact, sometimes life itself, right? We have the trees and forests, right? Let's look at some of them, which are essential, right? To do well in science. The first one is this. Can you see it aloud? Say it aloud. What is it? Yeah, scrupulous honesty and not fudging data. Have you done any experiments in the lab? You're not getting the expected data. What do? Put one here, put two here, put three there, right? Don't do that. That is called as fudging data, right? That's called as fudging data. Do not do it. If you want to do well in science, the first thing which is needed is absolute honesty. Saying that, like, if you don't know something, it's like, I don't know, man, chalega. That's okay. That is, I don't know, chalega. Like, one add kar de, two add kar de, right? Yeah. To make up things that won't work, right? I'll give you the primary example of this. See, I told you, right, in the 20th century, like quantum mechanics played to be a game changer, right? How much time have I? Yeah. So, okay. The thing is, you see, right, quantum mechanics, what happened was in the early 20th century, the experimental research was saying this. Well, I spoke about this is something beautiful, right? The experimental research, had like, it has a chadav and then like it just went down, right? Yeah. But then theoretical research, based on the physics of those days, it always went up. How long would it take, right? Okay, just to make it bring down, right? It was an easy thing to do, right? But the fact that they found that there was something wrong with the theory, that is what led to the invention of this whole thing called as quantum mechanics, right? Isn't it super profound? So had people been dishonest about this data, right, we wouldn't have had quantum mechanics. Of course, from your perspective, it's one subject less to study. But from our perspective, we wouldn't be having this talk today. Not just because I'm living because of quantum mechanics, but because a lot of this technology are built upon quantum mechanical research. Right? Yeah. So we have an impressive, list of applications using quantum mechanics. And all this because people dealt with things honestly. Right? Now time for a pop quiz. Who is this man? Who said it first? Yeah, okay, he is Max Planck, yeah. I was about to say, somebody would say it's Anupam Kher, okay, yeah. Oh man, how do you know Max Planck? How do you know Max Planck? You said so obviously. You read about him, exactly, good, yeah. So this is Max Planck, and it was this person, who didn't fudge the experiments. You know what he did? Like, he found that, okay, something is missing, so therefore I must change my theory somehow, such that, like the curve goes down. And that resulted in something super profound called as quantum mechanics, right? Yeah. So what is the next thing? The next thing is, this is something very important. We all, like at this age especially, we all hate to say that we don't know, right? We all hate to say we don't know, and we say, you know what? Right? If I say I don't know, like people will think that I'm bad. I'm stupid, right? It's perfectly okay to not know things. This is one more thing. It's something very, very, very important in not just science, but in a whole lot of other aspects also, right? So, what's a prime example of this? Do you know what this is? High reactive spectrum, right? Yeah. Okay, I'll come back to this, okay. Now the pop quiz is the following. Who is this person? Who said it first? Okay, yeah. You just saw the connection, right? Yeah. The high reactive spectrum, right? Yeah, excellent, yeah. So you do see, yeah. Give it to him. Hopefully, yeah. So again, so the point is this. What is the connection? So you all studied in your 11th standard, right? About the hydrogen atom spectrum, right? Yeah. And who proposed the idea? Niels Bohr. But he himself found out, right? He himself found out that his theory had flaws. He had to make up a lot of things. Like I said, right? With theory, you have to make up a lot of things. And he had to reconcile his theory with somebody else's theory, which is called as the Schrodinger's wave equation and other things, right? Yeah. Are you good, right? So the point is, that this person is not admitted to it. He said, you know what? आप लोग गलत है, मैं ही सही हूँ. Would quantum mechanics progress again, right? So the point is, it's super important. It's super important to realize that, you know, like we must be at any stage confess that I don't know. That's the first step towards knowing, right? Yeah. What are some other things? So this is something very important. What does it say? Yeah, carefulness in paying attention to the details. Matlab, like, you know, again, the same example, you know, I want to go home, right? Yeah. I want to go home, I go fast, I don't see a car coming in front of me, right? Yeah. We have to pay attention to details. In the life of a scientist, you know, like, paying attention to the details is everything, right? You must make sure that, you know, like, my observation makes sense. So that comes only if you do with passion, right? I'll give an example. For example, an example of paying attention to details is, you know, like, you guys are all here, right? I see so many people yawning. And I'm still, you know, continuing my lecture on and on and on, right? Which is obvious that I'm not paying attention to the details, right? Yeah, that's a perfect example, right? Yeah. Now, for example, you see, like, this is an experiment, you know, detected to detect electron spin. You know what electron spin is? You've heard about it, right? Yeah. This is actually one more thing super important, okay? Your spin, okay, your spin is not something, the electron spin, the spin quantum number, right? It has nothing to do with your spin the way you see, not like off spin, leg spin or something like that, right? This spin cannot be visualized. Repeat after me and again take it to your heart, okay? The electron spin cannot be visualized. This is something important, right? Yeah. So don't think, you know, like plus half, minus half, right? It is not off spin, leg spin, you know, like any of those things, right? Chinaman, whatever it is, right? It is actually, it cannot be visualized. That's something important. Now the question is, pop quiz, you know, name the people, you know, like who found out about this. Excellent, man. Yeah, I never expected, you know, yeah. Excellent. Wait, what names did you say? You said Goldsmith and who? Alan Beck. Well, actually, this is something else. Goldsmith and Alan Beck are close enough. You know, like, there are considered the people who like, I was not careful. They were the ones who proposed the theory for it, and these are the people who did experiment. Okay, yeah. But nonetheless, you deserve it. That's fine. Okay, good one. Yeah. So these were the ones who designed the experiment, and they were the ones who, you know, like, came up with the theory for it. Right? Yeah. And I tell you what, spin, you know, is something that has tremendous applications. Like, if not for spin, all your CD tape and like anything, watching a movie on a DVD, it will work. Because it's all works on what is called as spintronics. Right? And last thing, yeah, this is something important. You must all be open and willing to share your ideas. Right? It's not just one person alone, you know, cannot do anything much. Much progress cannot be made. Right? So, for example, you know, like, we speak of quantum mechanics, right? Quantum mechanics, you know, like had a tremendous difficulty in interpreting quantum mechanics. How do you actually interpret quantum mechanics? People have no idea. A lot of wise, old and young men and women had to come together and sit in a conference to understand quantum mechanics. And then this purpose is, you know, like, do you know the name of this conference? Sorry? Do you know the name of this conference? Most likely not, right? Okay, I'll proceed further in the interest of time. This is called as the Solvay Conference. Okay, you can Google it up. So, in what is called as the Solvay Conference, people had, you know, like, there's a second Solvay Conference, I believe, yeah. People had, like, discussed the most meaningful themes of quantum mechanics. And lastly, you know, yeah, this is something important. You know, like, how many of you feel that originality in life is important? Raise your hand. Yeah. I'm sorry to say that I disagree with you, okay. Originality is overrated. How do you be original, right? Can you know, like, instead of eating with your hand, you know, can you eat with our legs, right? Right? Originality comes up only after good scholarship. This is my point, right? We cannot be original in everything. Originality comes after you've paid enough attention to the details. That's something super important, right? Yeah. So people will tell you that be original, what. No. But be scholarly, pay attention to the details. That's much more important than, you know, like, being an original person. This is especially important as teenagers, okay? Please, you know, like, don't think that, okay, मैं अलग हूँ, मैं original हूँ, मैं अकेला रहूँगा. No. What's more important is, am I paying attention to each and every single step, right? That will make you be much more original at a later stage in life, right? Yeah. So, okay, the pop quiz is the easy one, okay, right? Yeah. What experiment is this? Okay, who should get the prize? Okay, the person who raised her hand there, okay, she deserves it first because she raised her hand first. Pass it along. That girl, whoever, I don't know, yeah. Alright, so the point is, this is the photoelectric effect, okay? But why do I care about this in this context? The point was, it was Einstein who came up with photoelectric effect, right? You all know this. But had Einstein, had Einstein not known about Planck's work, it was not just originality, it was originality with scholarship. Had he not known about Planck's work, how would he have done it, right? Are you clear, right? So the point is, originality is overrated. Good scholarship is much more important. And last one, this is the most important one, okay? Take a look at this. You can all get it, right? It's not about being cool for the sake of being cool, right? It's all about, oh, I won't work hard, at least, like do something, It's not about magic, it's all about the hard work, right? See, I'm speaking here, right? I'm spending so much energy, right? Yeah, it's hard work, it's not being cool, right? Likewise, right? Or I'll give you a better example. You're listening to me, right? It's not being cool, it's hard work, right? Yeah, it's the same way, right? Yeah, it's all in the hard work, okay, right? Yeah. Okay, quick question. What principle is this based on? What is it called? No, not of the principle. What's the next one? Sorry? Who said it? Who said it? What were you saying? Yeah, one more chocolate for him. Yeah. It is Polish exclusion principle, okay. But why this person? It's because this person, Wolfgang Pauli, right? This Wolfgang Pauli person was known to be, like a super, like a rigorous hard worker. He was of course smart, but he wouldn't skip any step. So, don't skip any step. So that's why, this guy who came up with this principle is super hardworking and a very high scholar, right? So the point is, don't worry about being cool and all that. Always work hard, especially if you want a career in science. These are something super important. Now see, so what did we see so far? Scrupulous honesty and not fudging data, good scholarship, originality is overrated, be careful and paying attention to the details, willingness to share ideas, admission of ignorance without ego, and it's all in the hard work, right? But where to listen? Of course, there are many more things like that, right? Yeah. But if you think about it, all these things, which we talk about in science, aren't these the same traits conventionally associated with being a good human being, right? That's the super most important point I'm going to tell you. Science should actually help you be a better human being, and not a more cocky person, right? That's the bottom line. Ultimately, if you're honest, people, you'll be trustworthy, right? That's when you'll be respected. Otherwise, who cares about you, right? Yeah, if you want to fudge data. And the thing is, if you're going to be more scholarly and if you pay attention to the details, you'll get so much more than someone who doesn't pay attention to the details, right? Your life is going to be much more enriched. And then, if you're willing to share ideas, you can appreciate diversity much more. And you'll get as a result so much. It's like, okay, I'm a person, I think in one way, I can't expect everyone to think, eat, behave in the same way, right? So diversity is something super important. And unless you're exposed to diversity, you may not even be appreciative of, a huge talent pool that's out there, right? And as a result, your intellect will be subdued. So this is also important. And see, you have to admit your limitations. Each of us has intellectual limitations. And if you don't agree to it, well, your opinions won't be valued much more. And lastly, it's all about hard work. The more you work hard, the more you can achieve things which you thought once as completely being impossible, right? And speak of human beings, right? These are some human beings who are pioneers, right? Who are pioneers in the field of computational chemistry, right? So even as recently as 2013, the Nobel Prize in Chemistry was won by these two gentlemen over here, Karpis, Levitt, and Washington, right? Yeah. And I must also say that the person who won the 1998 Nobel Prize, John Popel, he is my PhD advisor. So he's my academic grandfather, so to speak, So just a personal connection, bragging rights, yeah. So then so the point is, as recently as 2013, right, you have Nobel Prizes being given out to computational chemistry. The field is alive and is enriching, right? You see one more thing. The computational chemists we saw in the last slide were not Indians. But even in India, in this country, we have some astonishingly, well-respected computational chemists. The Nobel Prize is not the only aspect of good science, right? You understand? There are people who've done amazingly excellent work. For example, Professor Jemis from IISc Bangalore, Mr. Sarvapal was from NCL Pune, but is now at IISc Kolkata. Mr. Gadre from Pune University. Mr. Debashis Mukherjee from ISCS. Mr. Dev from Punjab University. Mr. Bakshi from IISc. Mr. Charushita from IIT Delhi. She passed away recently, but she was an outstanding computational chemist. And Mr. Satyamurthy was a director of IISc Mohali. Mr. Sebastian IISc. These are just some illustrative examples. There are many more, right? But I can keep saying, like each and everyone's name, right? Yeah. So these are people who've done some amazing work, being from India, right? And you can still achieve a lot. The Nobel Prize is just one thing, it's not the be-all and end-all of anybody's life. And see, why, like bring out these people, what's common between you and them? What's common? Sorry, being Indian is of course one, and then? Sorry? Human beings. Okay, that's common to any of us, right? Yeah. That's an unfair answer. Yeah. What do you think is a fair answer? Sorry? Okay, I'll tell you what I want. Okay. The point is that, at one point in time, they were all young like you, right? They were curious, ambitious, and wanting to excel, right? So make it talk on. It's not that hard to become anybody good, right? Just, be honest to yourself, right? Pay attention to the details, be a nice person, and most things will fall in place, right? Yeah. So with this, I'll leave you all, okay? Yeah. And the point is, what are the take-home messages from this talk? Yeah, expect some unexpected connections in science. So before this talk, right, you speak of computers, in chemistry. There is no chemistry between computers and chemistry, right? But hopefully after this talk, you understand that there is, a whole new underworld, right? Where, chemistry and computers are connected, right? Hopefully that is exciting. And then, and no big idea, right? No big idea can never be executed without carefully paying attention to the details. That's very important. And then, being a good scientist mostly parallels being a good human being. That's mostly, right? Yeah. Not always, exceptions do exist. Right? And, excuse me. Yeah. And lastly, don't imagine a scientist, as being some super crazy or super, obnoxious or super, geniuses or something, anything like that. They're as normal as you are, or they're as abnormal as you are. Right? Yeah. The point is, we're no different from anybody else. Right? Yeah. It's just it's a very normal trait. And lastly, my heartful thanks to the organizers. And if I had exceeded my time, my apologies. I thank the audience for patiently listening. And if you have any questions, get back to me. Okay, thank you.
Thank you. For 5 minutes. There is an announcement.
Oh yeah, sorry. Yeah. So this question. Yeah, your name first and then the question.
Good afternoon, sir. Myself, Arjun Kaushik, from 12th. So basically, most of the students aim for IITs, NITs and medical science, but very little of them aim for pure science. So can you tell about your experience based on pure science?
Yeah, okay. My experience with pure science. You want an honest answer or someone which should make you happy? What do you want?
Honest answer.
Honest answer is I didn't know. I didn't know and I didn't care. Okay, so the point was all I was thinking was 9th ke baad 10th, 12th ke baad 13th, right? Yeah. So I say, BSc ke baad MSc, MSc ke baad PhD, and that's all. I'll tell you what I cared about though, right? Yeah. I cared about questions which were close to my heart. I was like, okay, you know what? Why does this molecule react like this? I was crazy enough to enjoy that. You understand, right? I just, I just took care of the details. I never had in mind that, I never had in mind that I would join IISc Tirupati, right? I never had in mind that, I would come here, right? I would talk to you anything, right? These things happen. But what I do have in mind was that, okay, well, if I have to come here, I must work hard in preparing good slides, right? If I were to go to IISc Tirupati, then I must, make sure my research profile is good, right? So the point is, take care of the parameters which are in your hand. For example, be a good student, right? And don't allow peer pressure to get to you. This is what I would say, right? Yeah. Just do what you like. Just do what you like, but not just like what you like and what you're good at also, right? This is important. Sometimes you may like something, but you may not be good at it. It's a bit difficult in that case, right? So preferably like something you're good at, and vice versa, right? And keep paying attention to the details. I think things will fall in place more often than not. So if it is not a planned career, okay, right? It's not like, I always wanted to be a scientist. No. At your age, I was equally confused. Because I had so many options, right? In fact, back when I was a student, engineering was the rage. You were considered a bad student if you didn't do engineering. Right? Yeah. So this was about 15 years ago or something like that. Yeah. So the point being that there is no one answer for it all. Keep doing all the good things, conventionally good things, keep scoring good marks. Marks are important. So don't imagine that okay, you know what, knowledge is the be all and end all. I don't care about marks, right? Yeah. Marks are super important too. So is knowledge. Right? Yeah, so is knowledge. So gain both and see what comes your way.
Thanks, Mr.
Welcome, yeah. Any other question? Yeah.
So is there any connection between chemistry and maths other than computers?
Yeah, absolutely. Excellent question. That's something I'm not good at. That's why I didn't talk about it. Yeah. The connection between chemistry and math without computers is called as mathematical chemistry. Well, you just sit under a tree, right? You have a pen and a paper, you start writing things, and you solve the equations, and then those things exactly transfer into chemistry. It's called as mathematical chemistry. Great question. But I'm not going to be a mathematician. You actually, work out equations just with a piece of pen and paper, and then get problem solved. That does exist, yeah. Yeah. Alright, any more questions? Okay, the customary 2 questions are over for session then.